So, good evening, everyone. I welcome you all to the problem solving session number 4 for the course Biointerface Engineering. So, this course is basically being taught by the course instructor, Dr. Lalit Mohan Pandey. He is the associate professor in the Department of Biosciences and Bioengineering, IIT Guwahati. I myself am the TA for this course, which is NEPTIL PMRF TA. Myself, Shilpa. I'm also a PMRF in the Center for Environment, IIT Guwahati. So for this week's problem solving session, we are going to discuss about the week 4 assignment. We will go through the recap of whatever been taught in the week 4 as well as try to solve various questions that will help you to understand the problems of the week 4 assignment. So this is basically a doubts and interaction session which is held every week, that is every Tuesday from 7 to 9 p.m. If you have any queries, you all can raise your hand, or you can even unmute yourself and raise the query. So any question can be also posted in the chat box. So there is a particular discussion forum for the course which is available in the NPTEL portal. So any questions related to the live sessions conducted can also be asked there. So these questions will either be addressed in the forum or in the next week's live session. Right. So for this session, the outline of this live session would be particularly the week 4 course content recap, which will include the lecture number 10, that is protein adsorption, lecture number 11, characterization of protein adsorption, and lecture number 12, that is kinetics of protein adsorption. After which we will also discuss the week 4 related assignment questions and answer discussion. So let's move on with the week 4 course content recap, which first of all include the lecture number 10. We'll start with lecture number 10, that is protein adsorption. So in this lecture, we went through what is basically protein. That is, proteins are the building blocks of life, and they are the heteropolymers of 20 different amino acids which are linked together via a peptide bond. Now, as you can see in the figure, two amino acids are linked together with the help of a peptide bond. So this peptide bond basically contains a amide at one end, and on the other end there is a carboxyl end. So this bond is formed when there is the release of H2O. Next, the polypeptide chain which interact with itself gives the functional 3D protein structure. So basically there is a native and an unfolded structure, and the functionality of the protein is determined by its 3D structure. So there are basically 20 different types of amino acids which forms the basic unit of the protein, and the R group is responsible or which determines the functional group of the amino acid. Now, if we talk about the structure of the protein, the structural configuration of protein determines the function of the protein, as I said earlier, and these structures are stabilized by various bonds that includes hydrogen, sulfides, electrostatic, as well as various van der Waals interactions. So moving on, in the same lecture, it was also discussed about the classification of protein based on their 3D structure. So basically it is of three different types, that is fibrous proteins, next is globular proteins, and third is solvated and flexible proteins. So fibrous proteins have regular structure, that is helices, pleated beta sheets. Example you can see as collagen, keratin, myosin, which is present in muscle and connective tissue. And this fibrous protein are insoluble in water. Talking about globular proteins, these proteins have elements such as alpha helices, beta pleated sheets, and are sometimes unordered. Certain examples include biocatalysts such as enzymes, and various immunoreactions such as antibodies. However, these globular proteins are soluble in water. So fibrous proteins are insoluble, whereas globular proteins are soluble in water. Various solvated and flexible proteins are disordered coil-like structure, and such as glutenin present in wheat grains and casein present in milk. We also discussed various functions of proteins. What are the various functions of proteins? We'll go through it very quickly. So proteins are enzymes that react as enzymes that catalyze all biochemical reactions. They also help in transporting, that is ranging from electron transfer to carrying oxygen or hormones and various other substances. There are also messenger like proteins like hormones, integrins, and other immunoproteins such as antibodies. They defend against foreign invaders. Apart from several proteins are structural proteins. So basically, they regulate the elasticity and structure of the connective tissue and bones, as well as they help in mechanical work, that is in muscles. So various non-covalent interactions that can be seen in a protein structure are hydrophobic interaction, electrostatic interaction, dipolar interaction, dispersion interaction, as well as hydrogen bonding. Next in the lecture, we went through the hydrophobic interactions. So what are these hydrophobic interactions? These are basically the defined as the change in the standard molar free Gibbs energy during the transfer of R group from a non-polar medium to water. So the contribution of these hydrophobic interaction can be obtained by comparing the native unfolded structure and the native structure. So native structure which with known hydrophobicity of R groups. So the equation can be related as the change in the Gibbs free energy of amino acid minus the change in the Gibbs free energy of glycine. So why glycine here? So basically glycine has a functional group H, and hence we are comparing it with the native structure, that is native unfolded structure. So next is Gibbs free energy of transfer from non-aqueous to aqueous medium is approximately around 9 to 11 kilojoule per mole. So this Gibbs free energy, if it is greater than 0, the R group can be termed as hydrophobic, and if it is less than 0, the R group is termed as hydrophilic in nature. Talking about the electrostatic interactions, in the folded native structure, mostly all the charge is located at the exterior of the protein molecule, and this change in the Gibbs free energy of ion pairs can be given by G ion pair is equal to QiQj by 4 pi epsilon naught R square. Next, talking about the dipolar interaction, this we also discussed in the previous lectures. The dipole interaction is given by the equation mu is equal to Q into L, where L is the distance between two charges, that is plus Q and minus Q. So for standards, the dipole moment of water molecule is around 1.84 dBi, and that of an amide group is around 3.7 dBi. So next, dispersion interactions. So in this case, Gibbs free energy for dispersion force between two molecules at distance r can be expressed as Lj potential. This Lj potential was also discussed in first week course content. So which can be given as G displacement is equal to minus A by r to the power 6 plus B to the power B by r to the power 12. Next, there is hydrogen bonding present in proteins. This hydrogen bonding is basically present between an amide and a carbonyl group. sorry, it should be actually carboxyl group here. So there might be some spelling mistake. So for example, alpha helix contains strong hydrogen bonds between the carboxyl oxygen atom of the first peptide unit and the amide group of the fourth peptide unit. So basically one turn of alpha helix contains four amino acids. Also, in case of beta sheets, it can be either seen as a parallel beta sheet or an anti-parallel beta sheet. So this is also determined by favorable hydrogen bonds. So gives free energy for protein structure stability. So the folding of a polypeptide chain into the 3D structure of the native protein is the net result of interaction between segments within the protein molecule, but also between the segments of the protein and the environment. So the Gibbs free energy equation, you might all know that it's given as delta H minus T delta S, that is enthalpy minus temperature multiplied by entropy. And next, the entropy of conformation, that is S conformation, is given as Kb ln. So Kb ln pi, that is which is the number of distinguishable conformation. So Kb is the Boltzmann constant here. So talking about the protein stability in aqueous environment. So this is basically determined by comparing the native and the unfolded structure D. So native structure is represented by N and unfolded structure is represented by D. So this particular equation, that is delta N to D G, that is gives free energy for changing from a native structure to a unfolded structure, is given by delta H minus T delta S. So a negative value of this Gibbs free energy implies that the N state is less stable than the D state, and a positive value determines that N state is more stable than the D state. So this value usually varies between 20 to 60 kilojoule per mole. Next in the lecture, it was discussed about the factors affecting the protein stability. So various factors such as pH, ionic strength, temperature, adsorption properties, and presence of any other substances like denaturants basically are the various factors that affect the protein stability. So as in case, if there is a change in pH away from the isoelectric point, it increases the net charge density on the protein molecule and intramolecular repulsion, promoting the D structure, and vice versa. Whereas if you add any denaturant such as guanidinium chloride or urea, it basically increases the solubility of the apolar components in water and consequently promotes the formation of the D structure. So if we talk about the protein surface interaction, that is adsorption, there is basically two types of this interaction. One is physisorption and another is chemisorption. Physisorption is long range and weak intermolecular interaction like van der Waals interactions, whereas chemisorption includes short range and strong intermolecular interaction like covalent, ionic, and hydrogen bonds. So in case of temperature, if there is an increase in temperature, both delta H and delta S become more positive due to contribution from hydrophobic hydration to the heat capacity, resulting in low delta G. So this usually occurs due to the enthalpy entropy compensation. So protein structure is usually stable at an ambient temperature condition only. So the lower the temperature is, it can denature, or even at high temperature, it will denature. Moving on, moving on, we go to the lecture 11, that is characterization of protein adsorption. In this, we basically discussed about various techniques to determine the adsorbed protein. So there are three methods, including labeling method, colorimetric assays, and third is instrument based methods. So in case of labeling methods, there is radioisotopic labeling, then there is fluorescent labeling. Fluorescent labeling involves dyes such as fluorescein, isothiocyanate, and alexa dyes, as well as other techniques are staining. So various advantages and disadvantages can be seen from this table. Next, talking about the colorimetric assay, it in various methods such as Lowry protein assay, Bradford protein assay, or BCA, that is synchrononic acid protein assay. So in case of Lowry or Fallin protein assay, what happens is protein once reacts with Cu2 plus, it converts into Cu plus, that is making a complex with protein, that is protein Cu plus complex. When this complex reacts with the Fallin Kikuchi reagent, a blue colored solution is obtained, which can be measured in the wavelength range of 650 to 700 nanometer. So basically this blue color in the solution corresponds to the amount of protein present in the solution. Similarly, in Bradford protein assay, in this the cationic dye binds to aromatic and basic amino acids present in the protein. So which shifts the native maximum absorption from 465 nanometer, which is firstly brown in color, to 595 nanometer, that becomes blue in color. So the intensity of this color is directly proportional to the amount of the protein, similar to the case of Fallin protein assay. Next is BCA protein assay. In this case also, protein when reacts with copper, it converts into Cu3 plus. When this reacts with the BCA dye, it produces a BCA copper complex, which is purple in color. So this purple color solution can be measured at around wavelength of 562 nanometer. So again, the intensity of the color here is also directly proportional to the amount of protein present in the sample. Moving on to the instrument based methods. Wait a minute, just. Yes, moving on to the instrument-based methods. Several methods such as surface plasmon resonance, atomic force microscopy, quartz crystal microbalance, spectroscopic ellipsometry, SAXS, that is small angle X-ray scattering, and FTIR, that is Fourier transform infrared spectroscopy. These are various instrument-based methods that help in measurement of the adsorbed protein. So we will go through it very quickly. First is surface plasmon resonance. So in this case, when the plane polarized light is focused on the surface through a prism at a particular angle of total internal reflection, a small component of light, that is a light or a wave or field, penetrate the interface into the less dense medium to a distance of one wavelength. So the wave vector for this field is given as KEV is equal to omega naught by C eta g sine theta, where omega naught is the frequency of incident light, eta g is the refractive index of the dense medium, that is the prism, theta is the angle of the incident light, and c is the speed of light in vacuum. Similarly, the wave vector for the surface plasmon, that is KSP, is given as omega naught by C under root epsilon m eta s to the power square divided by epsilon m plus eta s to the power square, where eta m is the dielectric constant of the epsilon m is the dielectric constant of the metal surface, and eta s is the refractive index of the sample. So excuse me. We will next move on to the quartz crystal microbalance. In this case, it measures the change in mass per unit area by measuring the variance in frequency of the quartz crystal. So quartz crystal has piezoelectric properties, and the relation of the adsorbed mass, that is delta m, and the change frequency, that is delta f, is given by Sorbury equation, that is delta F is equal to minus 2 F naught square delta M by A under root mu Q and rho Q. So this F naught is basically the resonant frequency of the fundamental mode of the crystal in hertz. A is the area, rho Q is the density of the quartz, that is around 2.648 gram per centimeter square. Mu Q is the shear modulus of the quartz, which is given as 2.947 multiplied by 10 to the power 11 gram per centimeter square, a centimeter second square. So this delta M can also be written as minus C delta F by N. So this C is actually 17.7 Ng per hertz per centimeter square. So N is the overtone of the oscillation. Fine. We'll move on to the next instrument based methods, that is ellipsometry. So this is basically an optical measurement technique again that characterize light reflection from the sample. So in case of quartz crystal measurement, that was having piezoelectric properties, whereas in this case this have dielectric properties of the thin film, helps in measurement of the protein adsorption. So it measures the change in the polarized light upon light reflection on a sample, and this polarized light often becomes elliptical. So ellipsometry measures basically two values amplitude ratio, that is psi, and phase difference, that is between the parallel and the perpendicular light waves. So this the amount of protein adsorbed tau can be given as df, that is nf minus nl by dn by dc. So we'll move on to the next instrument. We have other two instruments left, that is one is FTIR and CD. So these are helpful in determination of the secondary structure changes in the protein. So FTIR is basically Fourier transform infrared spectroscopy. So the work based, it is based on the bond vibration for the adsorbed infrared radiation in the particular wavelength region, that is near IR region, mid IR region and the far IR region. So in case of FTIR, it basically works in the mid infrared region, which is actually 2.5 to 25 micrometer, which in case of wave number, if I say, then it is around 4000 to 400 per centimeter. So this 4000 to 400 per centimeter is basically the wave number. As you can see, this IR spectra is first deconflated and then fitted with a Gaussian curve. So in that case, secondary structures such as alpha helix, beta sheet, random coils and beta turn can be represented from the various wave number. That is, if it falls in that certain range of wave number, it can be represented as the particular secondary structure. For example, in case of alpha helix, if any peak observed in the range of 1648 to 1657, we will represent, or we can say that the peak classifies as the alpha helix. Similarly, the second table determines various amide regions and their approximate frequency, and have descriptions such as if the amide A that falls in the frequency of 300, then it can be termed as the NH stretching. So let's move on. CD. CD is that is circular dichroism. This is one of the most sensitive physical technique for determination of structure, as well as monitors the structural change of the proteins. So in this case, it involves the circularly polarized light. So unequal absorption of the R and the L components of the polarized light by chiral molecules are measured, and this also falls between two, that is far UV region and the near UV region. So far UV region is less than 250 nanometer and near UV region is greater than 250 nanometer. So far UV region, basically it is extremely sensitive towards protein structure, and near UV region reflects the contribution of the aromatic side chain as well as the disulfide bonds. Similar to FTIR, here also various wavelengths such as 222, 208 and 192 reflects the secondary structure such as alpha helix of the protein. So anytime we perform CD or FTR, we have to go through this table to know which peak belongs to which secondary structure. So we will move on to the lecture number 12, that is kinetics of protein adsorption. So this lecture basically talks about the adsorption of protein, that is the mechanism as well as the kinetics of it. So adsorption of protein occurs via it involves various interactions such as van der Waals interaction, Coulomb interaction, dipolar interaction. Other than that, hydrogen bonding, hydrophobic interaction, as well as there are several entropic based effects. So this protein adsorption consists of two major steps. One is the adsorption and desorption, and second one is the conformational adaptation, that is the rearrangement of the protein. So first step, as soon as it reaches the surface, it undergoes adsorption and then desorption, and meanwhile it also undergoes rearrangement. So if I define these steps uh, more in detail, so there are multi-step protein adsorption process that can be categorized into 6 steps. So first is the transport towards the interface. The protein molecule gets transport towards the interface. Next is deposition and attachment at the interface. Third, structural rearrangement, that is the relaxation of the adsorb molecule. So as soon as it touches the surface or the interface, there is various structural rearrangements that occurs within these adsorb proteins. Next is detachment from the interface. So this protein gets detached from the interface and gets transported away from the interface, and lastly possible restructuring of the desorb molecule. So there can be a possible restructuring, that is again a rearrangement or as restructuring of the desorbed molecule. So this kinetics is based on the similar adsorption processes. So wherein the transport towards the interface can be given by flux J, that is Cb minus Cs d by pi t to the power half, where Cb and Cs are the solute concentration in the bulk solution, that is the Cb, and Cs is the subsurface solute concentration in the subsurface region. D is the diffusion coefficient and T is the contact time between the solution and the solvent surface. So this flux J can also be written in the terms of KTR, where KTR is the mass transfer or mass transport rate constant. So KTR is J is equal to KTR CB minus CS. So basically attachment and reorientation can be given in the equation as P1 plus S, can be given as P1 S 1. So K1 is the rate constant here, and P is the protein and S is the subsurface surface. So there is end on attachment and then there is side on attachment. Similarly, based on these equations, rate equations can be also given. So we'll move on to the various first order reactions and the how rate equations and the solutions. So this basic table I have merged it from the lecture, so you can just go through it once. Apart from that, since this table was given in various slides and it was not merged as a table, I just tried to give all the rate equations as well as their solutions in a single table. So at the end of the lecture 12, we also went through the two basic uh, components, that is the rearrangement and intermolecular reactions. So when a protein or solvent interaction occurs, first it undergoes a dispersion reaction, and then if there is opposite charges on protein and solvent reaction, or there can be a similar charge on the protein and solvent. So Similarly, it can also then later undergo either hydrophobic surface interaction or a hydrophilic surface interaction. Then later on, then structural rearrangement in the protein can affect the intramolecular hydrogen bonding, that it can be increased or decreased, or it can decrease but compensate by protein solvent H bonding. Similarly, structural rearrangement in the protein affects the conformational entropy. So decrease, increase, or again increase. So a positive sign indicates the promotion of the protein adsorption, and a negative sign in this table refers to the resistance of the adsorption. Lastly, in the lecture 12, it was being taught about the competitive adsorption. For example, in this case, as you can see, the green colored molecule is represented as BSA molecule, whereas the blue colored circular molecule is the FB or IgG molecule. So first, as you know that in case of adsorption, there is first the side-on orientation, and then first there is an end-on orientation, and then there is a side-on orientation. So this is basically a Roman effect, that is displacement of initially adsorbed protein by a second protein. So it occurs due to the competition between two different protein. So the already absorbed protein, in this case such as the BSA molecule, gets displaced by the other protein, that is the IgG molecule. So you must remember what is this Roman effect and how this competitive adsorption works. So I think we have tried to get an overview for what was being taught in the week 4 course content. So we may solve certain questions relating to those particular three lectures, that is lecture 10, lecture 11 as well as lecture 12. So these are not actually the assignment questions which are being uploaded at the current state, but I have tried to add certain questions which will help you in solving those questions of the week 4. So we'll take 1 minute break, and then we'll start solving the questions. If you have any questions or any queries regarding the week 4 course content, you may just post it in the chat box, or you can also unmute yourself and raise the query. Okay, fine. We will try to solve the first question, that is question number 1, which is the amino acids of protein are linked with one another through dash bonds. So your options here given are: option number A is ester, B glycoside, C ether, and D peptide. So the amino acids of proteins are linked with one another through what kind of bonds? Ester, glycoside, ether, or a peptide bond?
Peptide bond.
Okay, fine. We have got the answer from Smriti, that is peptide bond. So we'll discuss what is the answer, and so the answer to first question is peptide bond basically. So I already discussed this while going through the recap of our session, that peptide bond is the bond between two amino acids. So As you can see from the figure, a peptide bond is formed by joining the carboxyl group of one amino acid to the amino group of another. So basically two amino acid, if they come close to each other, they form a peptide bond between the carboxyl group, that is the C double bond O group, the and the amino group of another, that is the NH group of another amino acid. So when this occurs, what happens? One molecule of water is also released. As you can see, HOH gets released from the during the reaction. That is while when a peptide bond is formed, one water molecule is released. Right. Other than that, ester, glycoside, and ether bonds, these are different types of bonds. For example, glycoside bond is present between two saccharide units. So we will move on to the next question. So the questions are, I have tried to keep the questions quite easy based on the uploaded questions in the week 4 course content, that is the current questions that has been uploaded in the portal. So the second question here is stable arrangement of amino acid residues resulting in alpha helix or pleated structure is a option A is primary structure, option B is secondary structure, option C tertiary structure, and option D is none of the above. So you have to see that what kind of stable arrangement of amino acid when occurs and it result in alpha helixes or beta pleated sheets, then what kind of structure does it result? So as you know, proteins can be characterized based on their structure in as primary or secondary or tertiary, and also it can be categorized as quaternary structures. So I will repeat the question again. A stable arrangement of amino acid, and amino acids when they undergo rearrangements and form a stable structure that results in alpha helices or beta pleated sheet is termed as either primary or secondary or tertiary or none of the above.
Secondary structure.
Yes. So secondary structure is the correct answer. We will see why secondary structure is the correct answer. So I hope you all are able to see the slide change. So secondary structure, that is option number B, is the correct answer. Why so? Since in case of primary structure, it is the most simplest form of protein that consists of a peptide bond, and it does not result in another structure, that is alpha helix or beta pleated sheets. But in case of secondary structure, the two folds that are extremely prominent in biochemistry of secondary structure are the alpha helix and beta pleated sheets. So basically, from the figure you can see the coil structure is the alpha helix, whereas the arrows are showing the beta pleated sheets. So the alpha helix is a right-handed helical coil that is held together by hydrogen bonding between every fourth amino acid. So basically, one turn of an alpha helix contains four amino acids, right? And in case of beta pleated sheets, there are two different regions of polypeptide chains that lie side by side and are bound by hydrogen bonds. So these two different regions of polypeptide chain can run either in parallel direction or also in anti-parallel direction. So, beta pleated sheets can again be divided into parallel and anti-parallel beta pleated sheets. So, I think this question is also quite clear and easier to answer. So we will move on to the next question, that is our question number 3. So the question number 3 is, in the tertiary structure, helices, sheets, bends, turns and loops. These are assembled to form A. Domain, B. Unit, C. Element or D. Cluster. So you have to answer in case of a tertiary sheet, when helices, sheets, bends, turns and loops, they assemble together, then they form what kind of? So they assemble to form either option A is domain, unit, B, C is element and D is cluster. So what kind of structure they form? These have a particular name. So you have to answer from among these four options, that in case of tertiary structure, various helices or sheets or bends and loops to form either A domain, B unit, C element and D cluster. Okay, so we will see what is the answer to this question is. So in case of tertiary structure, when these kind of units, that is helices, sheets, bends, turns and loops, they assemble, they basically form a domain. So the correct answer to this question is option number A, that is domain. So domains are the fundamental units of tertiary structure. So each domain contains an individual hydrophobic core built from the secondary structural unit that is connected by loop regions. So these domains are termed as the fundamental units, also gives the functionality of the structure, that is the functionality of the protein is determined by these domains. So these domains can either be alpha domain, beta domain, alpha plus beta domain, or lastly alpha slash beta domain. So these are present in four different types, that is alpha, beta, alpha plus beta and alpha slash beta domain. So unit is nothing. Unit I have added just to this is just added to make you all confused. Element, again, we cannot relate element with a protein. And lastly cluster also, we don't have anything such as cluster when we are talking about the protein structure. So we will move on to the next question, that is question number 4, which is, all of the following are interactions that stabilize the tertiary structure of a protein except for option A is hydrogen bond, option B ionic interactions, option C is peptide bond, and option D is van der Waals interactions. So you have to see which of the following interaction does not stabilize the tertiary structure of a protein. So one of the option among these four does not help in stable formation of the tertiary structure of a protein. So option A is hydrogen bond, option B is ionic interactions, option C is peptide bondings, and option D is van der Waals interaction.
Peptide bond.
Okay, I got the answer as peptide bond. So yes, option number C, that is peptide bond. This is one of the interaction that does not help in stabilizing the tertiary structure of protein. All the other three, that is hydrogen bonding, ionic interactions, and van der Waals interactions, are interactions that help in stabilizing the structure of a protein. So option number C, that is peptide bond, is correct. Apart from it, you can see that van der Waals interaction, hydrogen bonding, disulfide bonding also helps in stabilization of the tertiary structure of a protein. So these peptide bonds are majorly responsible for stabilizing the primary structure of the protein and not the tertiary structure. So the number and sequences elucidated of amino acids in the polypeptide chain constitute the primary structure, and the amino acids are linked with each other by this peptide bond only. So we discussed about peptide bond in the first question of our assignment 4. Okay, fine. We will move on to the next question, that is question number 5. So we have to choose the incorrect statement about the peptide bond out of the following. So we have been given four various statement, or you can say various characteristic of the peptide bond. You have to select the incorrect statement. So your options here are: option number A is partial double bond character, option B is trans in configuration, option C is rigid and planar, and option D is ionic in nature. So you will have to select one of the option among these four are is incorrect, that is false. So you have to think about what is peptide bond and what are the various properties of a peptide bond. So a peptide bond is basically a bond between two amino acid, which is at one end it is the carboxylic end, uh, that is the carboxyl end of one amino acid, and from another the amine group from other amino acid. So a peptide bond is basically CONH group. Okay. And does it have a partial double bond character? So yes, it has a partial double bond character. A peptide bond is actually having a partial double bond character. So first option, we may rule out the first option as it is the correct statement about the peptide bond. If we move on to the second option, that is trans in configuration. So what is trans in configuration and cis in configuration? Cis as in CIS, cis in configuration. If you may recall your basic chemistry from standard 11th, you may try to think about the structure and then compare whether it is trans or cis in configuration. So next option is whether it is rigid and planar. So I may also tell you this peptide bond is planar in structure. It is rigid as well as planar. So option number A and option number C, I have already given you that both of these are the correct statement. And lastly, option number D, that is ionic in nature. So you have to think what kind of bonding is it. Is it a ionic bond or is it a covalent bond? Okay, so let's see what is the answer. So the correct answer to this question is option number D, that is ionic in nature. So we had to choose the incorrect statement. So basically, it is having a partial double bond character and it is also rigid and planar. However, it has a covalent bonding. It is not ionic in nature. It is rather a covalent bond. So this peptide bond is covalent bond. You should remember that it is covalent in nature. And talking about the option B, that is trans in configuration. So if you look in the second figure, which has which is divided into A and B. So when you see figure number A, it has O and C alpha on one side of CN, that is the peptide bond, and C alpha and H on the other side of the uh, peptide bond. So this kind of structure basically represent the trans configuration, and the B, that is B figure, has O and H on one side and C alpha and C alpha. Both the carbon atoms lies on the similar side of the peptide bond. So this kind of configuration is termed as cis configuration. So if you compare uh, the structure A with the first figure, so you will find that the carbon lies, that is C alpha lies opposite on, that is on the either ends of the peptide bond. So this kind of configuration is termed as trans configuration. Fine. So in this case, option A was correct as it has partial double bond character. Option B is also correct as peptide bond is trans in configuration. Option C, that is peptide bond is rigid and planar. This is also a correct statement. However, option number D, that is a peptide bond is ionic in nature, this is probably the incorrect statement. So you now know what is the reason and how to give the answer to the question. Fine, we will move on to the next question. So question number 6 is R group in an amino acid is hydrophobic when the Gibbs free energy is greater than 0, the Gibbs free energy of transfer is less than 0. Option C, Gibbs free energy of transfer is equal to 0. And option D, none of the above. So in lecture number 10, uh, we have went through the recap for lecture number 10, and probably I also discussed about this thing there. So the Gibbs free energy, if you relate, Gibbs free energy of transfer is equal to Gibbs free energy of the amino acid minus Gibbs free energy of the glycine. Right, this was the equation which we went through during the recap of lecture number 10. So think about the same and try to give the answer to this question. So R group in an amino acid is hydrophobic when option A is Gibbs free energy of transfer is greater than 0. Option B, Gibbs free energy of transfer is less than 0. Option C, Gibbs free energy of transfer is equal to 0. And option D is none of the above. So if you go through lecture number 10. So here you can see how we determine the hydrophobic interaction, and I already said you that the hydrophobicity can be defined as the change in the standard molar free Gibbs energy during the transfer of R group from a non-polar medium to water, and hence the equation forms as the Gibbs free energy of transfer is equal to the Gibbs free energy of transfer of the amino acid minus that of the glycine. So at the end you can see it's written that Gibbs free energy of transfer, if it is greater than 0, then the R group is hydrophobic, and if it is less than 0, R group will be hydrophilic. Right. So if the amino acid is hydrophobic, obviously the Gibbs free energy will come out as positive, and if the amino acid is hydrophilic in nature, so from the first equation, as you can see, uh, this will come as less than 0 if it is hydrophilic in nature, and the total Gibbs free energy will be less than 0, right? Sweet. So our sixth question is, I guess, is now you can easily give the answer. So the answer to this question is option number A, that is the change in the Gibbs free energy of transfer when it is greater than 0. We term it as the R group is hydrophobic in nature, and if it is less than 0, the R group will be hydrophilic in nature. Okay, let's move on to the next question, that is question number 7. So for the transition of a protein from native to unfolded structure, if the standard Gibbs free energy, that is delta N to dg, is 45 kilojoule per mole, then the native state is more stable than the D state. Option B is the native state is less stable than the D state. Option C is no change of state will occur, or option D is none of the above. So native state is represented by N, and the unfolded structure or the unfolded state is represented by D. So when there is a transition from the native to unfolded structure, the standard Gibbs free energy is represented by delta N to G, N to D, G. In this case, if the value of this standard Gibbs free energy is 45 kilojoule per mole, what will you say about the native state and the D state? So whether the native state is more stable, or it is less stable, or there is no connection between the stability and the Gibbs free energy, or option D is none of the above. So this also, while going through the recap, we tried to describe about, or we tried to know about this standard Gibbs free energy. So this is also given in lecture number 10. If you go through the lecture number 10, you may probably able to give the answer to this question. So if we see, if we go back and check where did we discussed So we discussed this in the protein stability in aqueous environment basically. So how do we get the protein stability in aqueous environment? If we try to evaluate the delta G, that is the change in the Gibbs free energy, by comparing the native and the unfolded structure. So the delta G, as you all know, delta G is given as delta G is equal to delta H minus T delta S. So we have just written the delta G as delta N to D G, and similarly delta H and delta S is also written. So Gibbs free energy is equal to enthalpy minus T delta S. T delta S is entropy. So when the enthalpy is high, so the delta G will be also positive. If enthalpy is in negative, delta G will be also having negative value. So a negative value of this delta G will imply that the N state is less stable than the D state, and if there is a positive value of this delta G, then it will say that the delta N is more stable than the D state. So usually delta G value varies between 20 to 60 kilojoule per mole. So that is, this is a positive value, and when there will be positive value, the native state will be more stable than the unfolded state. So if we go back and answer this question, it will be, the correct answer to the question will be option number A, that is the native state is more stable than the D state. The value given here is 45 kilojoule per mole, that is, it is a positive value, and hence N state is more stable than the D state. If it would have been a negative value, the N state would be less stable than the D state. Fine, we will move on to the next question, that is question number 8. So question number 8 here is, in the protein classification, the globular proteins are dash in water. So in case of protein classification, the globular proteins are, option number A is insoluble in water, option B saturated in water, option C unsaturated in water, and option number D we have soluble in water. So this also we tried to recap it during lecture number 10, and classifying a protein, it was fibrous proteins or either globular proteins or solvated proteins. So you have to recall whether globular proteins are insoluble in water, or it is saturated in water, it is unsaturated or soluble in water. So if you try to recall, I said that fibrous proteins are actually insoluble in water, whereas globular proteins are soluble in water. So the correct answer to this question will be option number D, that is soluble. And option B and option C are just given to confuse you a bit, right? So if we see, the correct answer is soluble, and fibrous proteins are insoluble in nature and not globular proteins. You must remember that globular proteins are soluble in water, They contain different structural elements such as alpha helices, beta plated sheets, and for example, enzymes and antibodies are example of various globular proteins. And the apolar amino acid residues are mainly located in the interior, whereas the polar residues are primarily found in the periphery, and hence it is a globular in nature. So the correct answer will be option number D, that is soluble, and we may say that globular proteins are soluble in water and rule out the other options. Okay, we will move on to the next question, which is question number 9. Which of the following is true for chemisorption? Now again, you will have to recall what is chemisorption and what is physisorption, and what are the various interactions that belong to chemisorption as well as physisorption. So when a protein adsorption occurs or protein surface interaction occurs, it mainly occurs in two ways, that is chemisorption and physisorption. So your options here are, option A is short range and weak intermolecular interactions. Option B is short range and strong intermolecular interactions. Option C is long range and strong intermolecular reactions. And option number D is long range and weak intermolecular reactions. Sorry if I misspelled reactions, it should be interactions. So whether chemisorption is strong range and weak, or short range and weak, or short range and strong, or is it long range and strong, or long range and weak? So probably if you go back through the lecture recap, you will again find the answer. So this particular portion is also being discussed in lecture number 10, protein adsorption. So in the second box, that is the protein surface interaction, that is adsorption, you can see it is basically occurring in two ways, that is physisorption and chemisorption. So physisorptions involve long range and weak intermolecular interactions like van der Waals interactions, and in case of chemisorption it is short range and strong intermolecular interaction. This involves covalent bondings or ionic bondings or even hydrogen bondings. So you can see the enthalpy is around 20 kilojoule per mole in case of physisorption. So it is weak intermolecular interaction. And in case of chemisorption, it is around 200 kilojoule per mole. Hence, it is a strong intermolecular interactions. So now you can give the answer to this question very easily. So the correct answer would be, for in case of chemisorption, it would be short range and strong intermolecular interactions. That is option number B, right? So again, a certain question can come where you may be asked physisorption in case of chemisorption. So you must remember what kind of interactions are involved in both these cases. Even it may come that which of the following is a interaction present in chemisorption. So you might be given various interactions such as covalent, ionic, van der Waals or hydrogen. So you must remember all of these interactions. Fine. So we will move on to our next question, that is question number 10, which is which of the following range of wave number represents the alpha helix of secondary structure. So this is this question is quite incomplete if I say it should be like which of the following range of wave number represents the alpha helix of secondary structure while you are doing an FTIR. So FTIR has a standard table. Just let me. So your options here are option A is 1662 to 1686, option B is 1642 to 1648, option C is again 1648 to 1657, and option D is 1623 to 1641. So this is basically based on the standard table that you refer when you do an FTIR and when you plot the uh, infrared peaks in a Gaussian graph like Gaussian table. Okay, so I will just show you what is the table and you can relate to it then. So this is a particular table if you are trying to see which of your peak determines what kind of secondary structure. So I hope this is visible. So in case of secondary structure, the band assignment in water, if it ranges between 1648 to 1657 per centimeter, this is the wave number actually. Okay, so then it will constitute an alpha helix. Similarly, it is given for beta sheet, random units as well as coils. So if you compare the options, then you can see that option number C, that is 1648 to 1657, falls in the range that corresponds to the secondary structure, that is the alpha helix. Fine. So the answer to the question number 10 is option number C, 1648 to 1657. Okay, we will move on to the next question. So we have this question which is which of the following is not a colorimetric method for measurement of adsorbed protein? So your options here are A. Bradford assay, B. BCA assay, that is bisynchronic acid assay. Option C is Pauling Kikuchi assay, and option D is DPA, that is diphenylamine assay. So you have to answer that which one is not a colorimetric method for measurement of adsorbed protein. So while you are answering this question, please give me 2 minutes. I may get myself some drinking water. So fine, I think if you have thought about it, can you please try to give the answer to this question? That which of the following is not a colorimetric method for measurement of adsorbed protein? So your options are Bradford assay, BCA assay, that is bisynchronic acid assay, and option C is Pauling Kikuchi assay. So Pauling Kikuchi assay is also known as Lorry assay, that is Lorry method for determination of adsorbed protein. As I already gave you one of the hints that C is not an option. C is a colorimetric method, and it is, you can rule out the option number C, and option number D is DPA assay, that is diphenylamine assay. So colorimetric means color based assay in which the intensity of the color of the sample or the solution is measured at a particular wavelength. So thus the intensity of the sample directly proportional to the amount of protein present in the solution, right? So we already discussed this during the lecture 10 recap. So if you see, the correct answer to the question is option number D, that is diphenylamine assay, that is DPA assay. So in case of measurement of adsorbed protein, various colorimetric assays such as Lowry or Falling Kaikolshu protein assay, Bradford protein assay, BC assay are used, while DPA is among those colorimetric. It is also a colorimetric method. However, it is used for estimation of DNA and not protein. Fine. So option number D is not a colorimetric method for measurement of adsorbed protein. Rather, it helps in the estimation of DNA. Okay, we will move on to the next question, that is question number 12. So during adsorption of proteins in the quartz crystal microbalance, that is QCM, it is an instrument based method for determination of protein. So which of the following is correct? Option number A is dissipation factor D increases with time. Option B is dissipation factor D decreases with time. Option C is dissipation factor D is independent of time, and option D is none of the above. So you have to recall what was quartz crystal microvalence, and in that case this dissipation factor D, how does it changes when there is an absorption of protein, relating it to the time. So there is basically a graph that shows both the dissipation factor as well as the frequency. We will see what it is. That is, this graph is generally used when you are working with QCM. So if you can go back and think about, or this particular question is being picked from your lecture number 11, which involves the measurement of various adsorbed proteins. So you can, if you want, you can go back to lecture number 11 of your course, and you can easily answer it from there. So fine, we will see what the answer to this question is. So dissipation factor D increases with time during the adsorption of protein in QCM, that is quartz crystal microbalance. So during adsorption of protein on crystal surface, basically two things occurs. One is the frequency decreases due to mass increase, and second is dissipation factor D increases with time. So these two things you must remember while working with any questions related to quartz crystal microbalance will come. You must see how does a frequency change due to the mass increase, or how does the dissipation factor changes with respect to time. So as time increases, the dissipation factor D increases, as well as if there is a mass increase, there will be a frequency decrease. So F is basically indirectly proportional to the mass, and D is directly proportional to the time. Fine. We will move on to our next question, that is question number 13. So this is probably a numerical. So I usually keep all the last questions numerical. We have half an hour left. We will go through few of the numericals. Uh, so question number 13 is, in an adsorption experiment, following data were reported. Considering first order kinetics, determine the rate of adsorption. So your answer here are A 0.5618. So the rate of adsorption is K. So basically it won't be having any unit. Then there is B option, that is 0.2098. Option number C is 1.7 and option number D is 2.6. So this table is been given wherein time and adsorbed amount or adsorbed mass is given. So at 1 hour there is around 5 mg per meter square adsorbed mass of protein. Similarly, when at 2 hours there is 10 mg per meter square of adsorbed mass. So it goes on till 10 hours. So the data is given from 0 to 10 hour. So within that 10 hour, the mass has increased from 0 to 31 mg per meter square. So basically you have to determine taking in like you have to think that considering the first order kinetics, you have to determine the rate of adsorption. Okay, I think I will also solve this with you all so that focus lost. Okay, I think the network was disconnected for a bit, but we came back very soon. So, okay, I will try to solve this question. So, this question is basically based on the first order kinetics. So, usually what will happen, the reaction will be, we will get a equation as mt is equal to m max 1 minus e to the power minus kt, wherein mt is the adsorbed amount of or adsorbed mass of the protein at time t, that is 10 hour and sorry at a particular time t, and m max is the maximum amount of time, that is in this case it is 10 hours, fine. So m max is the amount or adsorbed amount of protein in mg per meter square at 10 hours, 1 minus e to the power minus kt. So the k is the rate of the adsorption which we are going to find, and again t is the particular time in which you are going to find the k. So for every hour, or in this case 1 2 3 4, as you can see 10 different k we can find, right? So we will solve the question. You all can also join with me. I hope this is visible here. Yes, it's visible. Ink it. Okay. So fine. So according to the table, if I write the table as soon as I can just draw. So time is given and your adsorb amount of protein is also given in mg per meter square. So 1 2 3 4 5, 6, 7, 8, 9 and 10. I think it is visible uh, at your end, right? Yes. Sometimes it may also lag behind, so you don't worry. I will get back to you. 15, then it is given 20, then it is given 22. At 6 hour it is 24, at 7th hour it is 28, at 8 hour it is 30, at 9 and 10 both it is 31. So what we will do is we will find the rate constant, that is k, based on this particular equation. Mt is equal to m max 1 minus e to the power minus k1 t. So if you see, at t is equal to 1 hour, if I see, what must be the mt? Mt value will be 5, right? And m max will be obviously 31, and this will be minus k1. Sorry, this will be minus k1 and t. So t here will be again, how much will it be? It will be 1, right? So t will be 1. So can you just solve this equation and tell me what is the answer coming out? What is the k coming here in? Okay, I'll see. So it will become 5 by 31 is equal to 1 minus e to the power minus k into 1, right? So how much is 5 by 31? If I shift this to this side and this to this side, then it will be something like, you can write it something like this: 1 minus 5 by 31, it will come around something 0.1612. So now you can easily determine what is the k. So minus k would be ln 1 minus 0.1612, which will come around 83 something. So k here will come as 0.175. So we got the k at t is equal to 1 hour. So similarly, we'll try to find what is the t at what is the k at 2 hour, then again 3, 4, and we'll go until 10. So I will try to solve it quickly. If you can, then you may also go on trying to find what is the k at each and every hour. So at we did for 1 hour. Now we can do for at t is equal to 2 hour. So at t2 it's mt is equal to 10, m max 31, 1 minus e to the power minus k into 2, right? So if we solve this, 10 by 31, and so we'll get something 0.3225, and then we will get sorry, and we can take out the k as 0.175. So we got the k at T2. Similarly, we can find for T is equal to 3R, T is equal to 4R, T is equal to 5R, and so on. So I will continue this. So you can also solve with me. You can check whether the answer that I am getting and you are getting are similar or not. So it may be also verified. Okay, let's see. I will solve this very quickly. So at T3 we have mt is equal to 15 minus k will come as ln 0.51753. So k will come around similarly at t is equal to 4 we will have right. So this can be written as 120 by 31 is 0.645 and minus k into 4. If we write this in terms of ln, it will come as 0.355. K will come as 258. I think you are able to catch. So basically what we are doing is we are trying to find the rate constant for each and every hour. So this can also be we can get the answer from a graph, but this is basically for making you understand um, how to solve this question based on this particular equation. So okay, we will move on at t is equal to 5r. So it will come as 22 is equal to 31. Again 1 minus e to the power k minus 5. So 22 by 31, it will come as 1 minus 0.709. Then minus k into 5 is equal to, this will be ln 0.291 and minus k will again, this will be minus k is equal to ln 0.291 by 5, which will be around so k will come as So you can use your calculator. Okay, here is 0.2468. So we will quickly solve the others also. Right now we did till t is equal to 5r. We have 5 more left. That is t is equal to 6. T is equal to 6r, which is 24. So minus k into 6 will be around. Okay, I will write this so that so basically becomes something as this. Next we have t is equal to 7r. This will be e to the power minus k into 7 will be ln 0.097, right? And then k will become something as minus 2.33 by 7. So here will be minus and k will be 0. We go forward. We have t is equal to 8r. I think you all are also getting how to solve this. So at t is equal to 8r, mt is 30 and m max is 31. 1 minus e to the power minus k into 8, right? So e to the power minus k into 8 will become 1 minus 0.967 and minus k into 8 will be, so k will be, minus k will be at around, and k will be, so for both t is equal to 9r and t is equal to 10r, what will happen is mt and m max will be equal, right? mt will be become equal to m max, and hence e to the power minus k into 9 will become 0 and e to the power minus k into 10 will also become 0. So k will be 0 here, right? So if we see all the, if we look at all the rate constant and try to average it out, we will get your k. That is the answer to the question we will get. So if we see, I am writing it for you on calculating the average K, we will get K will come as, you have to just add everything and divide it by 10, right? So this will be first K was 175, then we got 194, then we got 21199, then we had 2468, then we had plus 0.426 and plus 0, which we don't need to write, right? So this divided by 10. Can anyone average out and tell me what is the answer? So basically I have a calculator with me in my hand. You can also solve with me. Okay, we'll see what's the answer coming. So 0.258. So it is divided by 10. Basically, how much should be the answer? Is it coming around 0.2098? Write it down here. So this K is coming at around, so please verify if possible. If not, you may also do it later. Okay, we will now move on. I think there is no doubt in this particular question. If you have, you can ask it hereby. Fine, we will move on to the next question. That is our question number 11. Sorry, 14. So I hope you all were able to know how to solve this question. So mt is equal to m max 1 minus e to the power minus kt. This is in case of first order kinetics. Fine, we'll move on to the next question. Question number 14. So question number 14 and 15 are basically connected, and let's see what it is. So you have to assume that the backbone of a polypeptide in an alpha helix is completely fixed, whereas in the unfolded state, each peptide unit in the polypeptide can attain 4 distinguishable conformations. So you have to calculate the delta S for the transition from alpha helix to the unfolded state for a polypeptide consisting of 10 amino acids. So this particular polypeptide consists of 10 amino acids. So if you go back to lecture 10 again, there is particular equations given to find the entropy, that is delta S. S for S conformation is equal to R ln pi. Yes, it was something like S conformation is equal to R ln pi. Sorry, R ln sigma. It was R ln sigma. So your options here, answers are given: A 115.25 joule per Kelvin per mole. Option B is 115.25 joule per mole. Option C is 52.12 joule per Kelvin per mole. and option D is 40 joule per Kelvin per mole. So basically you have to also uh, see whether the units are matching or not. So in case of delta S, what should be the unit? From like, depending on that also you can think what can be the answer. So you have to assume that the backbone of a polypeptide in an alpha helix is completely fixed. Okay. So in the unfolded state, each peptide unit in the polypeptide can attain 4 different conformations. So you have to calculate the delta S for the transition from alpha helix to unfolded for a polypeptide consisting of 100 amino acids. Okay, so we will see how to solve this question as well. We are lagging behind of time. So this is the particular equation wherein from you can solve the answer, solve the question. So delta S is equal to R ln sigma. As I already told you that S conformation can be given as R ln sigma. So R ln sigma unfolded minus R ln sigma of alpha helix. So in case of unfolded state, a particular peptide unit can attain 4 different conformation. So here we have 10 amino acids. So each of the 10 amino acid can obtain 4 different conformation. Whereas for alpha helix that is already fixed also has 10 amino acids, but it cannot attain any different conformation, right? So we will see. Do you have any idea? I'll just go back and try to write the equation here. So delta S is unfolded state conformation minus the alpha helix conformation, right? So delta S is basically R ln S, sorry, so R ln sigma unfolded minus R ln sigma that of alpha helix. So if I take out the R, what will it become? Unfolded minus ln alpha helix. So you have any idea how, what value should we put at that of sigma unfolded and sigma helix, sigma alpha helix? So I already told you that in case of unfolded state, it can have 4 different conformations. So each amino acid can have 4 different conformations. Whereas in case of alpha helix, it is bound, or it is the backbone, and it is basically fixed. So it cannot have various conformation. However, again, it has 10 various amino acids, right? So what we can write is, we can write this as delta S is equal to R, and this can be written as ln 4 to the power 10 and ln 1 to the power 10. So I already told you 4 to the, why 4 to the power 10, because it can attain 4 different configurations, and the total number of amino acid present in the polypeptide is 10. Whereas in case of alpha helix, it has only a single conformation and it has 10 different amino acids. So if you solve this, you will be easily able to answer the question. So R is our gas constant. You may take it as 8.314. So if I write it, R is my gas constant, which is 8.314 joule per Kelvin per mole, right? So you put this value here, 8.314, and if you solve this, ln 4 to the power 10, and this one will come as 0, and this will come as 13.86, right? Can you verify once? How much will it come? It's 13.86. So if you multiply these two, how much will you get? So 8.314 multiplied by 13 point will come as 115.23. Fine. It will come something as 115.23 joule per Kelvin per mole. So I think we already have the answer with us. Going back, so option number A, that is 115.25 joule per Kelvin per mole, is the one which we were looking for, and we almost got approximately similar answer. I hope there is nothing to worry about in this question anymore. If you have any doubts, you may ask again. uh, I will repeat this for you if you want. Otherwise, we will move on to the next part of the question. The question number 15 is actually in continuation with question number 14. So I tried to divide it into two parts. So basically, question number 15 here is, in the solvent 111 trichloroethane, the transition occurs at 30 degrees Celsius. Now you have to calculate the delta H, that is the enthalpy per amino acid residue, if your delta S, that is the change in the entropy for the transition alpha helix to the unfolded for a polypeptide, is 115.25 joule per Kelvin per mole. So the delta S from the question number 14 is given in this question, and now you have to find the delta H. If you relate it with the standard equation of Gibbs free energy, how do you find the Gibbs free energy? So delta G is equal to basically delta H minus T delta S. Excuse me. So if you try to solve the question with that equation, probably uh, you already have your delta S as well as T is given as 30 degrees Celsius. So you have to find the delta H, right? So your options here are A, 34.92 joule per mole, B, 34 34922 kilojoule per mole, option C, 34.92 kilojoule per mole, and option D is 34,922 joule per Kelvin per mole. So again, there you have to take care of the units. The units also matter, right? Finally, we'll see what is the, so what the answer is actually C, that is 34.92 kilojoule per mole. And as I already said, you have to just focus on the standard equation of Gibbs free energy. Delta G is equal to delta H minus T delta S. So since it is a transition state, this will be again be equal to 0. So if we solve this question, so you can write delta H is will become equal to T delta S, right? T delta S will go on the other side and it will become positive T delta S. So you can easily find H. enthalpy, change in enthalpy as you have been given with the value of T and delta S. So T you must convert the centigrade value into Kelvin units. Here we will try to solve, right? So we have our delta G is equal to delta H minus D delta S is equal to 0. Now if you take this on the other side, you will get this. You already have T is equal to 30 degrees centigrade. Now you can convert it into Kelvin. How much it will come? 273 plus 30, it will come approximately 303 Kelvin. And you have been also given with the value of delta S, which is around 115.25. This is given in joule per Kelvin per mole, right? Yes, 115.25. So if you solve this, delta H will come as, how much is T? T is 303 multiplied by 115.25. So T here is in Kelvin and your delta S is in joule per mole per Kelvin, right? So K and K will cancel out. If you multiply these two, how much will you get? We calculate. So we will get the answer as 34,92075. So this is in terms of joule per mole. So if you go back to the answers, we have 34.92 in terms of joule per mole. So this is not the correct answer. We'll have to convert it into kilojoule per mole, right? Which is answer C. So if you convert this in terms of kilojoule per mole, so you divide it by, to convert this joule per mole into kilojoule per mole, you just have to divide it by 1000. So 92075. So approximately 34.92 kilojoule per mole. So we are here with our answer. I hope this question was also a straightforward one. So is there any doubt regarding this question number 15? If not, it's fine. Otherwise, even while studying the subject or going through the lectures, if you have any doubts, you may again post it in the discussion forum, or you can ask it in the next week's problem solving session, which will be again held in Tuesday from 7 to 9. So we got the answer to question 15. I'll wait for if you have any doubts, and then we will wrap up the session. So next Tuesday is 4th of April. So we will meet on 4th of April, same timing, that is 7 to 9 p.m. Okay, fine. I take it as you don't have any doubts. So you all can leave now. We will meet in the next session. Thank you so much for attending the session, and good night.